we're going to talk about modeling with quadratic functions. And in Algebra 1 we did modeling, but for many of you that's been 2 or 3 years ago since you've talked about real-world applications of quadratics. Today we're going to talk about using quadratic models to predict and to optimize. Almost always our solution will depend either on the intercept. So it might be the x-intercepts, it might be the y-intercepts, or the turning point, which is also known as the vertex of the quadratic model. And oftentimes in these types of problems, there's going to be lots of words in that. So there's certain statements or phrases that we look for to help us identify what we need to know. In this first part, if it says maximum, if it says minimum, if it says highest, if it says lowest, we're looking for the turning point, which I abbreviated TP for turning point, or the vertex of the quadratic. And today we're going to look more at how are we solving these algebraically. And since we're going to be solving algebraically, we're going to use that formula of x equals the opposite of b over 2a. A familiar equation. The opposite of b over 2a helps us find the x value of the vertex. And once we find the x value of the vertex, then we can substitute that back into the equation to find the y value, which again goes along with the turning point of the vertex. So again, maximum, minimum, highest, lowest. The other one, it might say, when does the something hit the ground? Or when does something hit the water? Or how long is something in the air? When we see those things, then we're looking for the x-intercepts of the function. And to find these, we go back to our old favorite, which is factoring. Solving by factoring. So let's look at our first example. It says the graph shows the height h in feet of a small rocket t seconds after it's launched. The path of the rocket is given by the equation h of t equals negative 16t squared plus 128t. Don't forget to include units with every answer. And the first one says, how long is the rocket in the air? Well, we started over here at 0, we went up, and then we went down. And how long is something in the air is just back there with our words here. It says when you see something like how long is the rocket in the air, we're looking for x-intercepts. And more specifically, we're looking at the intercept to the far right here, which is 8 seconds that the rocket's in the air. And what we're just doing is we're interpreting this graph. So the next question says, well, what is the greatest height the rocket reaches? So we're looking at our tallest point in this graph, which is so our highest point here is at the very top of this graph, and it looks like our increments of our graph go in 10, so this is 260 feet. And what time is it, or how long does it take us to get to that 260 feet? Well, the x-axis has our time down here, so as we follow our vertex point down to the x-axis, we see that it's 4 seconds. And the greatest height, and then at what time does it reach the greatest height, is our vertex, which is 260. That's the only value that I don't have units on. That's our vertex, our turning point. And then on letter D, about how high. So we might have to estimate on this one. About how high is the rocket after 1 second? Well, after 1 second, it looks like our point is about here, which is 100 feet. Do the same kind of thing for after 6 seconds. After 6 seconds, Oh, we already have a point on there. It's here, and that looks like it's 190 feet. And it's always nice when we have a picture given to us, because we can just try to read and interpret the graph as best as possible. The next part, it says state the time interval over which the rocket is going up. Well, when we start here, we're going back to some old things that you've heard a long time ago. When we start our graph here, we start going up, 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 up. Our graph is increasing. That's what it's looking at here. And when we're increasing, we're going to be increasing in an interval between where we started, which we started at 0, and when we get to the very top of our graph, and this is time, so this is going to be 4. So between 0 and 4 seconds is when we're going up. Notice that I didn't include in the start, I didn't include 0 and I didn't include 4. In between that time is when our graph is going up. We can also do the same kind of interval here when our graph is going down, 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 down. Well, at the very top of our graph, that's at 4 seconds. And when our rocket lands on the ground, it is over here at 8 seconds. So the interval where our rocket is falling downward is between 4 and 8 seconds. Finally, it says using the equation, find the exact value of the height of the rocket at 2 seconds. So we've got a good estimate here, but we can find the exact value. And for those of you who have the graphing calculator, you might want to use the store button. But this is height equals. And our equation is -16. And what we're going to do is we're going to put 2 in for the time. And then it's plus 128 times 2. So if you have the most basic of calculators, there's the computation to get the value. But I'd like to show you the store button again. And the store button here, what we're going to do is we're going to take 2 and store an x, enter, and then we type in our function. -16 x squared, which is t in our formula, but we're going to use x, plus 128x. And either way that we calculate it, we should get 192 feet for our height at 2 seconds. So it's nice when the picture's already drawn in for us. But as we flip our page, it's not always. So our model here for this second one is that Amy tosses a ball in the air in such a way that the path of the ball was modeled by the equation y equals -x squared plus 6x. In the equation, y represents the height of the ball and x represents the time in seconds. And the first thing that we want to do is we want to go to our calculator and we want to type in this function. So we come over here to our calculator, we're going to go to y equals, and we're going to type in -x squared plus 6x. The rest of the sentence said, for 0 less than or equal to x is less than or equal to 6. But let's look at the picture here. There's our picture. But what we really just want are the points from 0 to 6. So we can go to our table. And what we see is 0, 0, 1, 5. Watch out for the scale on our grid. 2, 8, 3, 9. 2, 8, 3, 9. 4, 8. 5, 5. 6, 0. We only want that part of our picture. We could see the rest. If we need more points, we can see them on our calculator. But there's our model of the ball being tossed into the air. And if we can get the picture drawn again, it's nice because we should be able to figure this out. But what I'd also like to show you is how do we figure it out if we don't have a graphing calculator? So as we look at the picture, the first question says, at what time x is the ball at its highest point? Well, here's our highest point. That point right there. And as we look at the graph, the time, which is along the x-axis, tells us that it's at 3 seconds. But what we also want to do here is we do want to do this algebraically. How do we compute this algebraically, especially for those of you who don't have the graphing calculator? Well, what we're going to do is we're going to use the formula of x equals the opposite of b divided by 2a. And what we see is that a is -1. It's the number in front of the x squared term. And b is 6, the number in front of the x. C is 0 if you want to get technical on this problem. So when we fill this in, we get x equals -6 divided by 2 becomes -1. Which ultimately means x equals -6 divided by -2. And -6 divided by -2 gives us the 3 seconds. So it can still be done without the graphing calculator here. And that is how long it takes us to get to the maximum height of our graph. Well, now the next question says, well, now that we know how long it takes, what is the maximum height? And I'm going to put over here on our graph, because it says illustrate this on the graph, that the highest point is the maximum height. And we can look at our picture. Now, since it's a partial point there, that sometimes gives people a little bit of trouble. But if you have the graphing calculator, you know that the answer this time is going to be the 9 feet. And how do we find that? Well, what we're doing is we're taking that 3 that we found in part B, and we're putting it back into our equation. So it was y equals -x squared, but now we're going to put the 3 in for the x, plus 6 times x, but we're going to put the 3 in for the x. And once we do that, then we can calculate. So you can type that in. Again, let me just show you with the store button that we can do 3 store x, enter, and then we can type in our function, -x squared plus 6x. You can just type it in. You just need to be really careful about the negative, but what we see there when we type it in is we do still ultimately end up with the 9 feet. So finally, it says algebraically determine the time when the ball reaches the ground, and then label this on our graph. So let's label where it hits the ground first, and it's here. I'll put hits ground at that point. It says algebraically determine that, and if you look back at the front page of your notes, when it says where does it hit the ground, what we're going to have to do is we're going to have to factor. And our function here, once again, is y equals -x squared plus 6x. But to use the zero product rule, we need to put 0 in for the y. And now we can factor. And we're going to use our greatest common factor. And the greatest common factor in this problem is x. And When we factor that out, we have negative x plus 6 equals our 0. And then we're going to set each of our factors equal to 0. So it's going to be 0 equals x, and 0 equals negative x plus 6. Sorry, you're probably running out of space a little bit. But we can add x to both sides. We get x equals 6. And which one of these two is the answer to the problem? Well, we labeled our picture. X equals 0 is back over here at the origin, at the far left of our picture. And what we're looking for is where it hits the ground. X equals 6. So it says, and in fact, it's looking to algebraically determine the time when. So in 6 seconds there, which matches what we say on our graph. But a decathlete at the Olympics throws a javelin such that its height, h, above the ground can be modeled as a quadratic function of the horizontal distance d that is traveled. Which of the following is a realistic quadratic function for this scenario? Well, first things first, when it's a multiple choice question, can we eliminate any of these answers? And the thing is, we need to know what a javelin looks like when it's going through the air. And the person throws it, and when they throw it, it kind of goes up and down. So it starts here, it goes up, and then it goes down. So knowing the general shape of this picture, can we eliminate any of the equations? And hard to see on the calculator, but eventually, if you typed in A, eventually it will look like this. It's disoriented over there, but it would look like this. And same thing with B. And the reason is because 1/100th is positive in that equation. So we can eliminate A and B because that's not going to model the direction that a javelin is thrown. So now we've got two choices. We've got C and we've got D. We actually had a similar problem on our review packet for our last test. The only thing that's different in these problems is one is +3 and one is -3. What do you think? Say it to yourself. Did you get C? Because it's the y-intercept is the important part here. It's the +3. -3 means we'd be throwing from underground. +3 at least gives us some height. Hopefully it's not 3 feet. Hopefully the javelin person is a little bit taller than that. But it means that on here, you're going to have a person with some height and then throw in the javelin. So our answer is C.